Hello students. Welcome. Welcome to next class, next video, next lecture, whatever you want to call it. It is all up to you. You all are great. I'm sure you all are doing great. You're gonna be great. You're the best. So you are the best. Just keep that in mind. And with that thought process, we'll continue with the class. Right. Case 4 we have seen, which is the case of constant positive acceleration. Great. So that we have done, if the acceleration is positive constant, the velocity will be increasing, and if it is a acceleration is positive constant, then velocity will be increasing at a constant rate. So we need a graph which should have a slope whose slope should be increasing at a constant rate. So basically increasing slope should be there if acceleration is positive, but it is positive as well as constant. So that condition is satisfied if we take an upward parabola, right? So keep in mind, for constant positive acceleration, the graph is an upward parabola, right? Next we have case 5. Now let us have a look at case 5 quickly. Fine. Case 5 is constant negative acceleration. Constant negative acceleration. Right. Now what happens in the case of constant negative acceleration? So since the acceleration is negative, that will mean that the velocity will be decreasing, and constant negative means the velocity will be decreasing at a constant rate. Now let us take the position time graph. Suppose this is the position time graph for constant negative acceleration we are trying to draw, right? So on y-axis you have position, on x-axis you have time. So constant negative acceleration means acceleration is negative constant, right? Negative constant, right? Acceleration is negative constant, that means the velocity will be decreasing, and velocity should decrease at a constant rate. Now how do we find velocity from position time graph? Slope, right? So if the velocity is decreasing, that means the slope must be decreasing. So how will be the graph for a decreasing slope? For decreasing slope, the graph will be a downward parabola like this. It can go further also, no problem. You can take a downward parabola like this. It can go all the way down as well, not an issue. This does not exactly look like a parabola, but yeah, something like this. So downward parabola will become a case for, what do you know? Downward, is it visible? Downward parabola, that's what we call it. Right, great. Fine. So we have seen all the cases now, I believe. Object at rest, object moving with constant positive velocity, constant negative velocity, constant positive acceleration, constant negative acceleration, right? Okay, let's go for the next part now. So we'll go for the next type of graph now. So these were all the cases that you need to keep in mind. Okay, so next type of graph will be the velocity time graph. And the second type of graph that we'll have is velocity time graph. Fine. Now let us see what happens in case of velocity time graph. So again we'll try to figure out what will the different things in velocity time graph give. So any graph, 3 things we are analyzing, as you are already aware. So let me just draw a velocity time graph just for our understanding, for internal reference, right? So this is velocity, this is time. So let us draw velocity time graph for our reference. So let us take a straight line like this. Okay, so in any graph we find 3 things, right? In any graph we find three things. The one is coordinate, right? So what will the coordinate of velocity time graph give? If I take any point here and if I take its coordinate, what will that give? So its x coordinate will be t, y coordinate will be v, right? So t comma v, fine. So what will the coordinate give? So coordinate of velocity time graph is going to give you velocity at any instant, right? What will the coordinate give? Coordinate will give velocity at any instant, fine, right? So that's about coordinate. Next we have the slope. So suppose the straight line will be making some angle with time axis. Suppose this angle is theta, right? So slope, what will the slope give? So slope is nothing but tan theta. So if I take tan theta will be basically here change in velocity by change in time, dv by dt, and dv by dt is nothing but acceleration. So what will the slope give? Slope will give you acceleration. Acceleration, right? Great. So the slope of velocity time graph at any instant is going to give you acceleration. And now we can also write the differential relation from here, which is also helpful while solving questions. So from here we can clearly understand that acceleration is nothing but dv by dt, right? So this relation also we can know. Since the slope of velocity time graph gives acceleration, then differentiation also must give acceleration, right? So that's that. Now moving ahead, finally we can also figure out what will the area under the graph give, right? So in the previous case, in case of position time graph, area did not used to give any meaningful quantity, you know? In case of position time graph, position into time is not any physical quantity. So what will the area under velocity time graph give? So area is roughly velocity into time, you know? Area is roughly velocity into time. So now area, and we also know that integration gives us area, you know? We also know that integration gives us area. So integration v dt, area will be integration v dt, fine. So when you integrate this, we are going to get area. Now roughly you think of area as velocity into time. Now what is velocity into time? Velocity into time is position or displacement, you say. So displacement is nothing but change in position. So the thing is, what's the thing? The thing is that area will give you change in position. Okay, area will give you integration of velocity, nothing but change in position. So area we can say is going to give you change in position, and that is nothing but displacement. In a way, that is nothing but displacement, fine. So area under velocity time graph is going to give you change in position, or you can say displacement, right? Great. Okay, moving ahead, right? And so from there we also got to know, we will also get to know the differential relation. So area is change in position, which is nothing but displacement here, and change in position, on the other hand, we can say change in position will be equal to integration, what? Change in position will be equal to integration v dt. So if you integrate velocity, you are going to get change in position. So that's that we need to keep in mind, right? Great, fine. Can you go for next part now? So we got to know that coordinate gives velocity at any instant, slope gives you acceleration, and area gives you change in position, which is nothing but displacement, right? Great, amazing. Okay, excellent. Now what we are going to do is, now we are going to see some cases, some different cases for velocity time graph. So let us see the first case. Case 1. Case 1 is object at rest. If the object is at rest, then how will the velocity time graph look, right? So case 1 is object at rest. Fine. Okay, great. So the object is at rest. How will be the velocity time graph? Very simple. The graph is very simple. This is what we are talking about, velocity time graph. And if the object is at rest, what will be its velocity? What will be the velocity of an object at rest? So if an object is at rest, its velocity at any instant will be 0, and the graph will be on time axis itself. So it will be a graph where the value of y coordinate at any instant will be 0, right? So in this case, object is at rest, so velocity is 0, acceleration is 0, anything. The main thing is the velocity is 0 at any instant. So the y coordinate at any instant should be 0. So that is sufficient to understand this. Or the slope should also be 0, because if object is at rest, velocity is 0, velocity is not changing, velocity is 0, constant. So acceleration should also be 0. And the slope of velocity time graph gives acceleration. Yes or no? So v is also 0, a is also 0. So the slope should also be 0. Right? So again, in a way, this line is parallel to time axis. Yes or no? So slope of this line we can say it is 0. Right? Wow, excellent. Now let us see the next one. Case 2. Case 2 is if the object is moving with, what is the object doing? Object moving with constant, object is at rest. If I take a case of constant velocity, if the object is moving with constant velocity, right? So if the velocity is constant, how will be the velocity time graph? So very simple. Let me just take this itself, right? Let me reuse this, it will save time. So how will be the velocity time graph if the velocity is constant? So depending upon how much constant it is, how much constant it is, in the sense, if the velocity is a positive constant, the graph will be like this. If the velocity is a negative constant, graph will be like this. And velocity can be 0 as well. 0 velocity is also technically constant velocity only, right? 0 velocity is also technically constant velocity, right? So amazing. So in this case, this is going to be positive velocity, this is going to be negative velocity, and this is going to be 0 velocity, and that's that, right? Okay, moving ahead. Case 3. So what is case 3 all about? Let us discuss. Fine. So object is at rest, object is moving with constant velocity. Next we have increasing velocity. So increasing velocity in the sense, how? If the object will have constant positive acceleration, increasing velocity in the sense constant positive acceleration. Let us take, so like if the velocity is increasing at a constant rate, so constant positive acceleration. Okay, object is moving with a constant positive acceleration, then how the graph will look like, right? Okay, so I have changed the setting a little bit, it should be constant. Fine. Okay, so again it's a simple case. Velocity time graph is there, constant positive acceleration. How do we find acceleration from velocity time graph? How do we find acceleration from velocity time graph? So slope of velocity time graph gives us acceleration. Yes, no? Slope of velocity time graph gives us acceleration. So pretty simple. If the acceleration is positive constant, slope should be positive constant, right? So it should be a straight line and the angle that it should make should be acute. Okay, so the graph will be something like this. Okay, this way. So here this angle theta should be acute. So theta should be less than 90 degree. Fine. So the graph can be any of these as long as the slope is positive, the angle that the straight line is making with time axis is acute, you are good to go, right? So for constant positive acceleration, the graph will be something like this. Next we have case 4. Case 4 we can take it as constant negative acceleration. So here space is little less. So 60% is sufficient, right? What happens? Is it shaking? No, right? Fine. So case 4, let us see. Let us take case 4, right? Great. Now what is case 4 about? Case 4 is about constant negative acceleration. Constant negative acceleration. If the object is moving with constant negative acceleration, then how will the velocity time graph look like? Okay, fine. Again, I'll take the same graph to draw it. Just I should not have actually, but anyhow, fine, no problem. So we have velocity time graph, constant negative acceleration. So we know that the slope of velocity time graph gives acceleration. So here acceleration is negative constant. So slope should be negative constant. Right, acceleration is negative constant, so slope should be negative constant, right? So in that case, the angle should be constant and obtuse. Should be obtuse and constant, right? Now, so how the graph will be? So it will be a straight line making obtuse angle. Okay, graph will be a straight line making obtuse angle. Fine. So this angle here should be obtuse. So this theta should be greater than 90 degree. So angle that the straight line will make with positive x-axis should be obtuse. So here also, like this angle, you can at any instant if you want to figure out how much angle the graph is making with x-axis or the time axis in this case, you can draw a line parallel to time axis like this. Fine. Then this angle should be greater than 90 degree. So that is how it will be for constant negative acceleration, right? Fine. Now case 5. Right. Case 5 is, now suppose if the acceleration is varying. No. So initially the velocity, you have seen object was at rest where velocity acceleration both were 0. Then we saw if the velocity is constant, then how things will be. So next we saw that if velocity is increasing, constant positive velocity means velocity is increasing. Yes or no? It's constant positive acceleration means velocity is increasing. Here the velocity is decreasing. Here acceleration is positive constant. Here acceleration is negative constant. Now what if the acceleration is varying? Yes or no? What if the acceleration is varying? If the acceleration is increasing, if any object is moving in such a way that its acceleration is increasing, you know, increasing acceleration. Fine. So how will the graph be if the acceleration is increasing? So simple thing, it should be a graph where the slope should increase. You know? It should be a graph where the slope should increase. Slope of velocity time graph gives acceleration. So if acceleration is increasing, that means the slope should be increasing. You know? So for slope to increase, the graph should be more like an upward curve. So the graph should be an upward curve like this. Right. And if you have decreasing acceleration, so it could be if the acceleration is increasing at a constant rate. So that again, that becomes jerk. You know? The rate of change of acceleration is called as jerk. So we'll be seeing that later. So if acceleration is increasing at a constant rate, then you can say that this will be an upward parabola, right? But here we are not saying specifically like that. It could be like if it is just increasing, so it can be any curve with an increasing slope, which will have a texture, or what can we say, a curvature similar to that of an upward parabola. Okay, so that's case 5. Next we have case 6. Case 6 is decreasing acceleration. Right, so something like this, a graph with decreasing slope, right? So here the acceleration is decreasing, so the slope should be decreasing. Okay, so decreasing slope means it should be a downward parabola or curve, a curve whose slope is decreasing. You know, the angle that it makes with time axis should be decreasing, right? Okay, great. Fine. So if acceleration is decreasing, the slope should decrease. If acceleration is increasing, that means the slope should increase. So that's that, right? Fine. We'll go for next part now. So next we have the last one, which is acceleration time graph, right? So let us see the last type of graph, which is acceleration time graph. So that's the third one, which is acceleration time graph. Fine. Now what happens in acceleration time graph? Let us talk about it. Huh? Let us try to understand acceleration time graph. So on y-axis you have acceleration, on x-axis you have time. So what happens in acceleration time graph? So in acceleration time graph, three things we have. First one is coordinate. So what will the coordinate of acceleration time graph give? Coordinate of acceleration time graph will give you acceleration at any instant of time. As simple as that. If I take any point here, x coordinate will be t, y coordinate will be a. So that is going to give you acceleration at any instant of time. That's it. Nothing less, nothing more, just acceleration at any instant of time, right? Okay, no problem. Okay, great. So what will the coordinate give? Coordinate will give you acceleration at any instant. Fine. Okay, great. Next we have, what do you find next? Next we find slope, right? So three things we have: coordinate, slope and area. What will the slope of acceleration time graph give? And if you talk about the slope of this thing, what will the slope of acceleration time graph give? So slope is tan theta, right? What is slope? So suppose here this angle is theta. So slope is tan of the angle theta, right? And tan theta will be nothing but dA by dt, right? It's like the differentiation also gives us slope, right? So now what is rate of change of acceleration? So rate of change of acceleration actually called as jerk. Okay, so jerk is nothing but rate of change of acceleration, or double difference d square v by dt square also you can say. Fine. So slope of acceleration time graph will simply give you the rate of change of acceleration. Clear? So generally we they don't ask question related to jerk. We don't study this physical quantity according to the standard syllabus wise, but yeah, you can obviously keep it in mind, right? Next we have area. The last thing that we calculate here is area. Now what will the area under acceleration time graph give? Yes or no? So how do we get area? Area we get by integration. Area we get by integration. So area here will be integration a dt. So if I integrate acceleration with respect to time, we are going to get area, right? And what does that area do? What it does, what it gives us? So let us try to follow up on that. So area acceleration into time. So what is acceleration into time? Acceleration into time, you can say velocity, or the more appropriate thing to say will be change in velocity. Fine. So area under acceleration time graph is going to give you change in velocity. Fine. Now this is very important in fact. Fine. So area gives change in velocity. So likewise, if you write in terms of differentiation, integration of acceleration, integration of acceleration with respect to time. I'm talking about integration here. So integration of acceleration with respect to time is going to give you change in velocity, right? Clear? Okay, great. Change in velocity means v minus u, final velocity minus initial velocity, you can say, right? Clear? Okay, we'll go for next part now. So now let us see some cases for acceleration. So case 1, so here there are not many cases, right? So case 1 is, what is case 1? Case 1 is object at rest. Okay, how will be the acceleration time graph if the object is at rest. Simple thing, if the object is at rest, or one more case you can take, or if it is moving with constant velocity, right? If the object is at rest, or if it is moving with constant velocity, right?